Look up at the night sky on a clear evening, and you might feel a familiar sense of wonder. That vast darkness, sprinkled with countless stars, holds secrets we've only begun to uncover. Among those secrets, few cosmic structures capture our imagination like the majestic barred spiral galaxies, swirling islands of stars, dust, and mystery, where gravity and chaos dance in perfect harmony. These grand designs aren't just beautiful, they are living puzzles, each one telling a story of creation, evolution, and forces we are still striving to understand. And there is one galaxy in particular that stands out even among these celestial wonders, NGC 1300, located over 60 million light-years away in the constellation Eridanus. This stunning barred spiral isn't just another pretty face in the cosmos. It's a treasure chest of unexplained phenomena, a place where the normal rules of astrophysics seem to twist and bend in ways that leave astronomers both fascinated and humbled. From its unusually quiet core to strange star-forming regions that defy expectations, NGC 1300 challenges what we think we know about how galaxies live and evolve. In this video, we're going to journey deep into the heart of this extraordinary galaxy, exploring 30 of its most baffling and mesmerizing mysteries. We'll uncover why its central supermassive black hole appears silent when it should be roaring, examine the bizarre structures hidden within its spiral arms, and question what lies behind its unexpected pockets of dark matter. This isn't just a tour of pretty pictures, it's a detective story written across the cosmos, and you're invited to join the investigation. So settle in, open your mind to the possibilities, and let's explore the enigmas of NGC 1300 together. Our exploration begins at the very heart of the galaxy with our first strange phenomenon, the eerily silent giant at the core of NGC 1300. In most large galaxies, the central supermassive black hole is a beacon of violent activity, a cosmic engine of unimaginable power. As immense clouds of gas and dust are pulled in by its gravity, they don't just vanish quietly. They swirl into a superheated disk, a maelstrom of matter that screams across the electromagnetic spectrum with intense radiation before crossing the point of no return. This process, known as active accretion, is why the centers of many galaxies shine with the brilliance of billions of stars, becoming what astronomers call active galactic nuclei. But NGC 1300 central black hole is different. It's strangely, profoundly quiet. Observations across various wavelengths, from radio waves to X-rays, reveal a darkness, a lack of the energetic outbursts we fully expect to see from a gravitational monster of its size. It's as if we're listening for the roar of a lion and hearing only a faint whisper. This presents a fascinating puzzle for scientists. Why is this particular beast so dormant? One compelling theory suggests this black hole is simply starving. For a black hole to shine brightly, it needs a steady diet of material. It's possible that the specific dynamics within NGC 1300 beautifully structured spiral arms are actually too efficient at organizing matter. The very processes that create its stunning symmetrical appearance might be preventing sufficient gas from funneling all the way down into the galactic center to feed the waiting giant. The black hole could be in a period of prolonged famine, left dormant and dim because there's simply nothing nearby for it to consume. Another intriguing possibility is that our view is being blocked. We are observing NGC 1300 nearly face-on, giving us a spectacular view of its spiral structure, but potentially looking straight down the throat of a dense, dusty torus, a giant donut-shaped cloud surrounding the central region. This thick shroud of gas and dust could be absorbing all the high-energy radiation coming from the accretion disk, effectively muffling the black hole's activity and making it appear quiet from our distant vantage point. It would be like seeing a brilliantly lit city from far away on an extremely foggy night. You know the lights are on, but the glow is completely diffused and hidden. This unusual quietness makes NGC 1300 a critical case study. It challenges our models of how galaxies and their central black holes co-evolve. By studying this silent giant, astronomers are forced to ask deeper questions about the life cycles of these cosmic phenomena and what truly triggers their periods of violent activity and profound sleep. Yet the mystery deepens when we consider the location and structure of these emissions. They aren't emanating from the galaxy's busy core or its violent, star-forming regions, but from seemingly quiet and unremarkable areas within its majestic spiral arms. This placement makes it incredibly difficult to attribute the signals to any kind of known catastrophic event. Supernova, for instance, leave behind vivid, expanding remnants of hot gas and dust, and the collisions of dense stellar corpses like neutron stars produce brief, incredibly intense bursts of energy followed by a predictable afterglow. The signals from NGC 1300 don't fit that pattern at all. They are more like a persistent, rhythmic beacon flashing from the cosmic darkness without any visible source or cause. This peculiar behavior has, quite understandably, led to a spectrum of hypotheses, some resting firmly within established astrophysics and others venturing into far more speculative territory. On the conventional end, scientists are investigating the possibility of an entirely new class of stellar object. Perhaps we are witnessing the activity of a magnetar, a type of neutron star with an unimaginably powerful magnetic field, but one that is behaving in ways we've never documented before. Its rotational period or precession could be creating a lighthouse effect that we simply don't have the models to explain yet. Alternatively, the source could be something even more exotic, like a system of interacting objects whose combined emissions create this strange, repeating pattern. Then there is the more provocative question that inevitably arises with unexplained, structured signals from deep space. Could this be something artificial? The speculation about a potential technological origin, while always a last resort in scientific inquiry, is a testament to how truly baffling these signals are. The concept of a beacon, whether intentional or simply a byproduct of some immense astro-engineering, is a staple of science fiction, but the rules of scientific investigation require us to exhaust all natural explanations first. This line of thinking, while thrilling, is a path we tread with extreme caution, as history has shown that cosmic mysteries almost always reveal a new natural phenomenon rather than evidence of other civilizations. Nevertheless, the very fact that such ideas are discussed highlights how these emissions from NGC 1300 push the boundaries of our current understanding and force us to consider all possibilities, no matter how remote they may seem. Just when we think we're starting to grasp the rules that govern galaxies like NGC 1300, another profound mystery emerges, one that strikes at the very foundation of modern astrophysics, the curious case of the missing dark matter. This invisible substance, which we cannot see but know exists through its immense gravitational influence, is thought to be the cosmic scaffolding upon which all galaxies are built. It's the hidden glue that holds them together, preventing their rapidly spinning outer stars from simply flying off into the void. For a majestic barred spiral like NGC 1300, our models predict a very specific and massive halo of this dark matter, a vast, unseen sphere enveloping the entire visible structure to explain its rotation. But the measurements tell a different story. When astronomers meticulously map the rotation curve of NGC 1300, that is, they plot how fast stars and gas clouds at different distances from the center are orbiting, they find something deeply puzzling. In most galaxies, these rotation curves remain flat far out into the outskirts, a telltale sign that there must be a huge amount of unseen mass dark matter, providing the extra gravitational pull to keep those high-speed outer objects in check. In NGC 1300, however, the observed rotational speeds in its outer regions don't quite match the powerful gravitational pull that a standard dark matter halo should be providing. It's as if you were swinging a ball on a string and it was moving at a speed that should break the string, yet somehow it doesn't, except in this case the string itself seems to be missing. The dynamics suggest that for its size and mass, NGC 1300 might be operating with a significantly smaller dark matter budget than our cosmological models would predict. This discrepancy forces scientists to consider several fascinating possibilities. The first is that our measurements could be incomplete or misinterpreted. Determining the precise mass and rotation of a galaxy millions of light years away is an incredibly complex task. Perhaps there are vast, faint streams of stars or clouds of neutral hydrogen at the very outermost edges of NGC 1300 that we haven't yet detected, material that would account for the missing gravitational influence. It's possible we simply haven't seen the full extent of the galaxy's mass. Another, more revolutionary idea is that our understanding of dark matter itself might need an update. The prevailing model, known as cold dark matter, posits that these particles are slow-moving and cold, clumping together easily to form the halos we base our predictions on. But what if the dark matter in a galaxy like NGC 1300 interacts with itself or with normal matter in ways we haven't yet accounted for? Perhaps certain galactic environments or formation histories lead to dark matter distributions that are far less concentrated than our standard simulations suggest. A third, and perhaps most intriguing, line of thought involves the unique structure of NGC 1300 itself. Its prominent bar is a massive engine that transfers energy and angular momentum throughout the galaxy. This constant gravitational pushing and pulling from the bar might have fundamentally reshaped the distribution of both visible and dark matter over billions of years, effectively scattering the dark matter halo into a much larger and more diffuse configuration than we typically find in other spiral galaxies. The very thing that makes this galaxy so visually stunning, its magnificent bar, could be the very mechanism that has hidden the signature of its dark matter from our current methods of detection. This missing signature isn't just a minor anomaly, it's a direct challenge to our models of how the universe constructs its largest and most beautiful structures. Moving from the galactic scale of missing dark matter, we zoom in closer to the vibrant spiral arms of NGC 1300, where another enigma unfolds in the very process of stellar creation. Here we find our fourth strange phenomenon, a deeply puzzling and anomalous pattern of star formation. In a typical spiral galaxy, you expect a certain logic to the cosmic nurseries. Vast clouds of cold gas and dust, nudged by density waves or shock waves, collapse under their own gravity to ignite new stars. This process should create a somewhat predictable tapestry, with star birth glowing brightest in the densest regions of the arms. But NGC 1300 defies this expectation in a spectacularly uneven way. Its arms are a patchwork of extreme activity and profound silence, where regions of explosive starburst activity lie immediately adjacent to vast, quiescent voids of gas that show virtually no signs of giving birth to new suns. It's as if you walked from a roaring, densely packed city center directly into a silent, empty desert within just a few city blocks. This sharp, IRREGULRR Chinese letter poses a significant challenge to our understanding of what triggers, and just as importantly, what suppresses, the most fundamental creative process in the universe. Scientists are actively investigating what could be causing these intense, localized bursts of star formation. The galaxy's magnificent central bar is a prime suspect. This massive structure acts like a cosmic conveyor belt, relentlessly funneling immense amounts of gas and dust inward from the outer disk. As these torrents of raw material pour down the bar and crash into the inner regions of the spiral arms, they create incredibly dense pile-ups. Imagine a logjam in a river where debris accumulates into a tight, chaotic mass. In galactic terms, this compression can be so violent and sudden that it triggers runaway gravitational collapse, igniting what are known as starburst regions, areas where stars are born at a rate hundreds of times faster than in our entire Milky Way galaxy. This bar-driven fueling could easily account for the brilliant, fiery knots of newborn stars that light up specific segments of the arms. However, this compelling theory only solves half the puzzle. It explains the where of the explosive birth, but not the why not elsewhere. Why do other areas brimming with seemingly ample supplies of cold gas remain stubbornly dormant and dark? The answer may lie in the subtle and complex physics of stellar feedback and magnetic fields. In the vibrant starburst zones themselves, the very first generation of massive stars to form live fast and die young. They flood their surroundings with intense ultraviolet radiation and powerful stellar winds, which can actually heat and disperse the surrounding gas clouds, effectively shutting down star formation in their immediate vicinity by preventing further collapse. This creates a self-regulating and perhaps self-limiting feedback loop, but this doesn't fully explain the large-scale quiet zones. Another powerful inhibitor may be at work: the galaxy's magnetic field. Invisible to our telescopes but detectable through its influence on polarized light, a strong magnetic field can weave through a gas cloud, providing a supporting force that counteracts gravity. Think of it as a cosmic web that holds the cloud up, preventing it from collapsing in on itself to form stars. In the tranquil regions of NGC 1300 arms, the magnetic field may be exceptionally strong and orderly, acting as a powerful brake on star birth and maintaining the gas in a state of suspended animation. The galaxy becomes a cosmic battlefield where opposing forces, gravitational collapse versus magnetic support and stellar feedback, clash, and the outcome in any given region determines whether it will blaze with new light or remain a dark, silent reservoir of potential. This bizarre patchwork challenges the very idea that star formation is a straightforward process, revealing it instead to be a delicate and finely balanced dance between countless competing factors. Now we come to a phenomenon that truly bends reality, forcing us to question the very fabric of space-time around this galaxy. NGC 1300 acts as a powerful gravitational lens. This is an effect predicted by Einstein, where a massive object's gravity warps the space around it, curving the path of light from even more distant galaxies that lie behind it from our point of view. This cosmic trick creates distorted, magnified, and often multiple images of those background objects, like a flaw in a giant lens. For astronomers, this isn't just a curiosity. It's one of our most powerful tools for weighing galaxies, as the degree of distortion directly maps to the total mass causing it, including the all-important dark matter. But with NGC 1300, the map doesn't match the territory. The lensing distortions we observe are far more pronounced and complex than what we should see based on the combined mass of all the visible stars, gas, and the predicted dark matter halo we just discussed. It's as if we're seeing the magnifying effect of a much heavier lens than the one we've been able to find. The light from those distant galaxies is being bent by something we cannot directly see, a gravitational signature of mass that appears to be missing from our inventory. This anomaly points to one of two groundbreaking possibilities, each more fascinating than the last. The first possibility is that there are hidden structures of dark matter within and around NGC 1300 that are far more lumpy and concentrated than our standard cosmological models allow. Our simulations often predict a relatively smooth and symmetrical distribution of dark matter, but the lensing data here might be telling us that the reality is much more intricate. There could be enormous, unseen subhalos of dark matter, vast clumps of this mysterious substance orbiting within the main halo, whose extra gravitational pull is contributing significantly to the lensing effect without giving off a single photon of light. Discovering such a structure would revolutionize our understanding of how dark matter behaves and clusters on the scale of individual galaxies. The second possibility is even more profound. What if the anomaly isn't with the mass itself, but with the rules of gravity? Einstein's theory of general relativity has been spectacularly successful for a century, passing every test from the orbit of Mercury to the detection of gravitational waves. However, those tests have largely been confined to our solar system or to the universe at its very largest scales. The environment within a galaxy like NGC 1300 could be a crucial middle ground where the rules might need a slight tweak. Alternative theories of gravity, like modified Newtonian dynamics or MND, propose that on the scale of galaxies, gravity doesn't weaken quite as quickly as Newton or Einstein predicted. This modification would explain the rotation curves of galaxies and the gravitational lensing anomalies without the need for any dark matter at all. The distorted light around NGC 1300 could therefore be a vital piece of evidence in one of the biggest debates in modern physics, a potential crack in the foundation of general relativity that suggests our understanding of the universe's fundamental force is still incomplete. Just as the gravitational lensing effect challenges our understanding of mass and gravity, another layer of mystery is revealed not by the absence of light, but by an overwhelming and peculiar presence of it. Across the vast expanse of NGC 1300, space-based infrared telescopes have detected a pervasive, enigmatic glow, a wash of infrared radiation that blankets the galaxy and defies easy explanation. Every star, every warm cloud of dust emits some level of infrared light, which is essentially heat radiation. Astronomers have highly sophisticated models that predict exactly how much of this glow should be present based on the number of stars and the amount of dust we can see. But for NGC 1300, the numbers simply don't add up. There's a significant excess, a mysterious infrared background hum that is far more intense than what the known ingredients of the galaxy should be producing. It's as if we've walked into a room, counted every single light bulb, and yet the room is still inexplicably brighter than our calculations say it should be. This surplus of infrared energy points to sources of heat that are completely hidden from our view in optical light. One leading hypothesis points to a previously unsuspected population of stellar infants. We could be seeing the collective warmth of vast, dense cocoons of gas and dust where stars are being born. These nurseries could be so deeply embedded within dark molecular clouds that their visible light is completely absorbed and reprocessed into the infrared glow we detect. In this scenario, we're not just missing a few stars, we might be missing entire generations of them, their brilliant light smothered at birth by their own dusty blankets, only revealing their existence as a faint heat signature. This would mean our current census of star formation in NGC 1300 is drastically incomplete, and the galaxy is actually far more active and fertile than it appears. Another fascinating possibility involves the very end of a star's life rather than its beginning. The galaxy could be filled with the faint, warm remnants of dying solar systems. As stars like our Sun reach the end of their lives, they shed their outer layers, creating vast, expanding shells of gas and dust known as planetary nebulae. These shells are warmed by the fading stellar core at their center and glow brightly in the infrared. A larger-than-expected population of these ancient, fading stars could contribute significantly to the overall infrared excess, painting a picture of a galaxy with a unique and unexpected demographic history. Yet the most exotic theories venture beyond conventional astrophysics altogether. Some scientists have speculated that this persistent infrared background could be a signature of something entirely new, such as the decay or interaction of hypothetical exotic particles. If dark matter is indeed made of weakly interacting massive particles, some models suggest they could annihilate upon collision with each other, converting their mass directly into energy, including gamma rays and eventually lower-energy infrared radiation through secondary processes. The diffuse, all-pervasive nature of this glow could therefore be the first faint signal of dark matter particles slowly destroying themselves throughout the halo of NGC 1300. While this remains a highly speculative idea, it illustrates the depth of the mystery. When observations defy all standard explanations, we are forced to consider possibilities that lie at the very frontier of physics, using the galaxy itself as a laboratory for discovering the fundamental rules of our universe. And just when we think we've seen all of NGC 1300 contradictions, we encounter a dynamic that seems to defy the very logic of a spinning galaxy: vast streams of gas that are moving in completely the wrong direction. The majority of the galaxy's immense structure, its billions of stars, its dominant dust lanes, its primary reservoirs of hydrogen gas, all rotate in a harmonious, coherent direction, a unified flow that defines the galaxy's spin. But detailed spectroscopic observations have revealed something astonishing. Tucked within the outer disk and halo are isolated clouds and filamentary structures of gas that are stubbornly, definitively rotating in the exact opposite direction. It's as if you were watching a mighty river flow steadily to the sea, only to discover a powerful, persistent current within it suddenly reversing course and flowing backward upstream. This phenomenon, known as counter-rotation, presents a stunning violation of the galaxy's overall symmetry and forces us to ask how such rebellious motion could possibly arise and, more importantly, how it manages to survive. The existence of these counter-rotating clouds points to a dramatic and violent history. Galaxies are not born in isolation. They grow over billions of years by consuming smaller neighbors, in a process astronomers call galactic cannibalism. The most compelling explanation for this backward motion is that these gas clouds are the lingering debris from a past merger, the final remnants of a much smaller dwarf galaxy that was captured and torn apart by NGC 1300 immense gravity. If this ill-fated satellite galaxy approached from a retrograde orbit, meaning it was orbiting in the opposite direction to NGC 1300 spin before it was captured, then the gas it donated to its larger captor would retain that backward momentum. This would leave these new clouds of material as a fossilized record of that ancient collision, a ghostly imprint of a smaller galaxy that was consumed long ago, whose final breath now spins defiantly against the cosmic current. But the real mystery isn't just how these clouds got here, it's how they've managed to persist for so long without being assimilated. In the dense, dynamic environment of a galactic disk, forces like dynamical friction and hydrodynamic drag should, in theory, work to quickly erase any such counter-rotating motions. The rebellious gas should collide with the vast majority of gas that's rotating the correct way, losing energy and momentum until it finally gives in and joins the dominant flow. The fact that we can still clearly detect these counter-rotating signatures means they have somehow avoided this fate for potentially billions of years. Their survival suggests that the gas in the outer disk of NGC 1300 is far less mixed and turbulent than we assumed, or that these clouds exist in relatively isolated pockets protected from the erasing effects of constant collision. They are cosmic holdouts preserving a memory of a violent event that would otherwise have been completely lost to time. This persistence offers astronomers a rare and valuable window into the galaxy's evolutionary past. By studying the chemistry and density of these counter-rotating clouds and comparing them to the galaxy's primary gas, scientists can effectively perform a galactic archaeological dig. The unique chemical fingerprint of the gas, its specific ratios of elements like oxygen, nitrogen, and carbon, could tell us about the nature of the dwarf galaxy it came from, such as how many generations of stars it had lived through before the merger. The stability of these structures also provides critical data for testing the viscosity and overall dynamics of the interstellar medium within a barred spiral galaxy. refining our models of how gas behaves, evolves, and ultimately fuels the birth of new stars over cosmic time. These backward-flowing rivers are more than just a curiosity. They are living fossils preserving a chapter of NGC 1300 history that would otherwise be completely invisible to us. While the galaxy's odd gas flows tell a story of its ancient past, our next phenomenon points to something happening right now, a rhythmic and powerful signal that defies all conventional explanation. Deep within the vast, sparse halo that surrounds NGC 1300, instruments designed to catch the universe's most violent explosions have detected something bizarre, a series of periodic gamma-ray bursts. Gamma-ray bursts are typically the birth cries of black holes or the collision songs of neutron stars, events so cataclysmic they are almost always singular and random, unleashing in mere seconds more energy than our Sun will produce in its entire 10 billion-year lifetime. But these bursts from NGC 1300 are different. They are repeating. They arrive with a strange, clock-like regularity, a precise cadence that is utterly unprecedented for such high-energy events. It's the difference between hearing a single, devastating explosion and hearing a metronome ticking in the void, each tick representing a blast of energy that can briefly outshine every star in the galaxy combined. This precise timing is the core of the mystery, as it immediately rules out most known astrophysical causes. A collapsing massive star can only die once. It cannot produce a recurring signal. The collision of two neutron stars is a final, destructive act that leaves behind only a black hole. For a signal to repeat on such a predictable schedule, the source must be an object that is somehow surviving these unimaginable energy releases, something stable enough to power a cyclical cataclysm. This has led scientists to investigate some of the most extreme and exotic objects theorized in astrophysics. One compelling candidate is a special type of neutron star known as a magnetar. These are remnants of supernova with magnetic fields so powerful they could strip information from a credit card halfway across the solar system. A magnetar undergoing powerful starquakes, sudden ruptures in its incredibly dense crust, could potentially release enormous blasts of gamma rays. If this magnetar were also precessing or wobbling on its axis like a slowing top, that wobble could bring its beam of energy into our line of sight at very regular intervals, creating the illusion of a periodic burst. Another fascinating possibility involves a binary system of incredibly dense objects. Picture a black hole and a neutron star locked in a tight, frantic dance. As they orbit each other, the black hole's immense gravity could periodically strip away layers of material from the neutron star's surface. Each time this stolen matter spirals into the black hole's accretion disk, it could ignite a massive outburst of gamma rays. The orbital period of this deadly dance would then become the timer for the bursts we observe. This scenario would require a perfectly tuned and stable system, which is rare but not impossible, and it would represent a type of interaction we have yet to directly confirm. Yet the sheer power and perfect regularity of these signals push at the very boundaries of what we believe is physically possible for any natural object. This has inevitably led to the most speculative and perhaps most thrilling line of inquiry. Could this be a signature of technology? The concept of a beacon, an intentionally constructed signal, is a staple of science fiction, but it is one scientists must consider with extreme rigor when all natural explanations fall short. The idea is not that the entire galaxy is an artificial construction, but that within its halo, a Kardashev-type 2 or 3 civilization might have built an energy source or communication device of unimaginable scale. Perhaps we are seeing the waste heat or directed energy from a Dyson sphere-like structure, or a so-called stellar engine used to propel a star system, operating on a cycle that produces these regular bursts as a byproduct. It is crucial to emphasize that this is the hypothesis of absolute last resort, a placeholder for "we truly have no idea." but the very fact that it can be seriously discussed highlights how profoundly mysterious these signals are. They stand as a direct challenge, a cosmic puzzle box that compels us to either discover a new class of celestial object or to radically expand our understanding of what might be possible in the universe. Building on the ghostly signals and backward-flowing gas, we now turn our gaze to the vast, empty spaces between galaxies, where an even grander and more mysterious architecture is suspected to exist. Our ninth strange phenomenon involves the potential discovery of dark matter filaments connecting NGC 1300 to its cosmic neighbors. According to our most successful models of the universe, galaxies aren't isolated islands but are woven into an immense, invisible structure known as the cosmic web. This web is thought to be composed primarily of dark matter, forming vast, thread-like bridges between the dense hubs where galaxies cluster. For a galaxy like NGC 1300, which is part of a larger group, we would expect to see hints of this underlying scaffolding. Recent gravitational lensing studies and detailed maps of the galaxy's outer velocity field have provided tantalizing yet controversial evidence of these faint tendrils. The data suggests there might be faint, linear structures of gravitational influence, invisible roads in the sky that appear to link the galaxy directly to others in its local group. If confirmed, this would be a monumental discovery, providing a direct glimpse into the hidden skeleton of the cosmos. However, the strange part isn't just their potential existence, but their precise and unexpected alignment. The suspected filaments don't seem to be oriented randomly. Instead, they show a peculiar coherence with the orientation of NGC 1300 magnificent bar. This is deeply puzzling because the cosmic web is thought to form on scales far larger than any individual galaxy, dictated by the initial conditions of the universe after the Big Bang. The evolution of a single galaxy's internal structure, like the formation of a bar, happens much later and on a much smaller scale. For these two vastly different systems, one intergalactic and one galactic, to share an alignment suggests a profound connection that our current models of cosmology and galaxy evolution simply do not predict. It's as if the growth of a tree were somehow directed by the layout of entire mountain ranges. The scales of influence are so different that they shouldn't be directly linked. This bizarre alignment forces scientists to confront some radical possibilities. One is that our understanding of how galaxies form within the cosmic web is fundamentally incomplete. Perhaps the flow of dark matter along these primordial filaments doesn't just provide the raw material for a galaxy to grow. It might also impart a specific spin or angular momentum that dictates the galaxy's internal evolution for billions of years to come. In this scenario, the bar of NGC 1300 didn't form randomly. Its very orientation might have been locked in place by the direction of the dark matter river that fed the galaxy's birth, a fossilized echo of the universe's largest scale structure manifesting in its beautiful spiral pattern. Another, more speculative idea is that these filaments are not entirely dark. They could be faintly illuminated by processes we are only beginning to understand. Some theories suggest that the weak but pervasive magnetic fields that might exist throughout the cosmic web could accelerate charged particles, causing them to emit a faint synchrotron radiation that would be nearly impossible to detect with our current technology. Alternatively, the decay or interaction of the hypothetical dark matter particles themselves within these dense filaments could produce a subtle glow of gamma rays or other radiation. If we could find a way to see this light, it would transform these theoretical structures from gravitational ghosts into visible, tangible features of the universe. The implications of confirming these filaments are staggering. They would provide the first direct observational evidence for the cosmic web's filamentary structure, which has so far been inferred primarily from computer simulations. For cosmologists, it would be like seeing the blueprint of the universe for the very first time. It would also offer a new way to probe the nature of dark matter itself. By studying how matter flows along these filaments and how they interact with the galaxies they connect, we could learn about dark matter's properties, whether it's cold, warm, or possesses some other, yet unknown characteristic. The mysterious alignment with NGC 1300 bar remains a tantalizing clue that the universe's largest structures and its most beautiful galactic details are intertwined in ways we are only just starting to imagine. And now we arrive at a mystery that strikes at the very heart of how we understand the composition of the cosmos, one that comes not from what we can see but from the unique fingerprint of light itself. When astronomers direct their most powerful spectrographs toward NGC 1300, they break its light down into a rainbow of wavelengths, creating a spectrum that acts as a cosmic barcode. Each element in the universe, when heated or energized, emits or absorbs light at specific, precise wavelengths, leaving behind a series of lines like a unique signature that allows us to identify it from millions of light years away. We have meticulously catalogued the spectral lines for every element on the periodic table, from the most common hydrogen to the most obscure artificially created ones. Yet, in the spectrum of NGC 1300, there are lines that defy this entire library of knowledge. They are emission lines that sit at wavelengths that do not correspond to any known atom, molecule, or chemical compound. It's as if a master painter had created a beautiful masterpiece, but upon close inspection, you find a color used that doesn't exist anywhere on any known color wheel. The immediate and most thrilling possibility is that we are seeing the signature of a new, unknown form of matter. This could be an exotic state of plasma that only exists under the unimaginable gravitational pressures near the galaxy's quiet central black hole or within the furious hearts of its starburst regions. In these extreme environments, the rules of atomic physics as we know them could be bent. Electrons might be forced into bizarre, high-energy orbits that are completely unstable here on Earth, creating transient energy states that emit light at these never-before-seen wavelengths. We could be looking at the fingerprint of matter operating in a regime that our laboratories simply cannot replicate, a glimpse into how elements behave when they are not just under pressure, but under the influence of forces we can barely comprehend. A more conservative, yet still profound, explanation points to common elements behaving in uncommon ways. The culprit could be something as simple as iron or oxygen, but existing within a plasma that is so rarefied and thin that it's what astronomers call optically thin. In this state, collisions between atoms are so infrequent that electrons have time to jump to energy levels that are usually forbidden in denser environments here on Earth. These forbidden lines are a known phenomenon in astronomy, but the specific wavelengths detected in NGC 1300 don't match any of these established forbidden transitions either. This suggests we might be seeing an entirely new set of forbidden lines, which would itself be a major discovery, revealing new intricacies about the delicate dance of atomic physics in the near-perfect vacuum of interstellar space. Then there is the most revolutionary idea of all, that these lines are not from a new state of a known thing, but from a fundamentally new thing itself. Some physicists have speculated that this could be evidence for a completely new element, one that is stable only under these immense cosmic conditions or one that has a vastly different atomic structure. While the periodic table is considered complete for stable elements up to a certain point, the frontiers of nuclear physics are always expanding. Alternatively, and even more speculatively, these lines could be a signature of dark matter itself. If dark matter is not a single inert particle but a whole complex sector with its own interactions and energy states, perhaps what we are seeing is the indirect glow from dark atoms or dark molecules annihilating or decaying into visible light. This would be a discovery of epochal proportions, providing our first direct window into the physics of the dark universe that makes up the majority of everything that exists. The persistence of these unexplained lines makes them more than just a curiosity. they are a direct challenge to our models of atomic and particle physics. Every time we point a telescope at NGC 1300 and see those same unidentifiable spikes in its spectrum, it is a humbling reminder that our knowledge of the universe, however advanced, is still incomplete. This galaxy is not just showing us what we don't know, it is actively pointing toward entire chapters of physics that have yet to be written. Now we turn our attention to the ancient guardians of galactic history, the globular clusters, and find a void where we expect a multitude. These dense, spherical collections of hundreds of thousands of ancient stars are like fossils from the earliest days of a galaxy's formation. Most large galaxies, including our own Milky Way, are surrounded by a retinue of these glittering swarms, often numbering in the hundreds. They are considered a standard part of a galaxy's makeup, a baseline population that tells us about the conditions during its birth. Yet when astronomers count the globular clusters orbiting NGC 1300, they come up short. The galaxy appears to possess a significantly smaller family of these ancient clusters than any model predicts for a barred spiral of its size and mass. It's as if a grand royal court was expected to have 100 honored knights in attendance, but upon arrival, only a few dozen are present, leaving us to wonder what happened to the rest of the entourage. This deficit points toward a dramatic and violent historical event. The most compelling theory is that NGC 1300 experienced a major merger in its deep past, a catastrophic collision with another sizable galaxy. While such events often trigger bursts of new star formation and can even create the conditions for a bar to form, they are also incredibly disruptive to the delicate gravitational dance of orbiting objects. The immense tidal forces generated during a galactic collision would have acted like a cosmic wrecking ball, violently stripping away a large portion of NGC 1300 original globular clusters and flinging them out into the intergalactic void, lost forever. Alternatively, the clusters themselves could have been torn apart and assimilated, their stars scattered into the galaxy's halo, effectively erasing them from the census as distinct objects. The missing clusters, therefore, could be the silent evidence of a traumatic chapter in the galaxy's life, a ghostly signature of a colossal impact that reshaped its very foundations. However, another, more sinister possibility exists closer to home. What if the clusters weren't stripped away by a past event, but are instead being consumed by a present danger? We've already discussed the galaxy's mysteriously quiet central black hole, but its dormancy might be deceptive. It could be in a cycle of fasting followed by a sudden, violent feast. As globular clusters orbit the galactic center, they can occasionally be dragged by dynamical friction into a doomed path that brings them too close to the central supermassive black hole. The incredible tidal forces from the black hole would then shred the cluster apart in an event called tidal disruption, swallowing its stars and adding their mass to its accretion disk. If NGC 1300 black hole has been through periods of actively consuming entire globular clusters, it would explain both the lack of these clusters today and the potential for strange, violent activity in the core that we might have missed in our cosmic timeline. The silence we observe now could simply be the calm after a feast. A third explanation challenges our understanding of the galaxy's very origins. Perhaps NGC 1300 didn't form with a small number of clusters. Perhaps it formed in an unusual environment that was inherently poor in the raw materials needed to make them. Globular clusters are thought to form from immense, dense clouds of primordial gas. If the region of space where NGC 1300 was born was unusually quiescent, or the gas was too hot and diffused to collapse into such dense knots, the galaxy may have simply started life with a smaller population. Its formation history would be unique, setting it on a different evolutionary path from its very beginning. This would make NGC 1300 a rare example of a galaxy that grew to a majestic size through a relatively peaceful and isolated history, rather than through the violent mergers that typically build such large structures. The missing clusters, in this case, aren't a sign of a violent past but of an unusually quiet one. Each of these theories tells a completely different story about the life of this galaxy, and by studying this absence, astronomers are piecing together the biography of a cosmic giant. But the intrigue of NGC 1300 magnetic fields deepens when we map their orientation. In a typical spiral galaxy, we expect the magnetic field lines to loosely follow the optical spiral arms, dragged and twisted by the rotation of the galaxy and the motion of its gas. It's a chaotic, turbulent process. In NGC 1300, however, the fields exhibit a startling degree of order. Over vast regions, particularly along the length of its massive bar, the magnetic field lines are not chaotic at all. They are incredibly well organized and aligned, running parallel to the bar itself with a uniformity that is frankly difficult to explain. This is like expecting to see the confused swirl of iron filings around a handful of magnets, but instead finding them all lined up in perfect, parallel rows like soldiers on a parade ground. This precise alignment suggests a governing influence that has overridden the natural turbulence of the interstellar medium, imposing a large-scale order that our current models of galactic magnetism simply don't predict. So what force could be responsible for creating and maintaining this mysterious cosmic order? One compelling theory points back to the galaxy's most dominant feature, its bar. This massive structure doesn't just move stars and gas, it also acts as a gigantic magnetic organizer. As the bar rotates, it drives shock waves and systematic flows of material throughout the inner galaxy. This relentless motion could be stretching and shearing the magnetic field lines, effectively combing them out until they are all aligned with the bar's own orientation. In this scenario, the bar isn't just a collection of stars, it's a giant dynamo itself, a cosmic generator that amplifies and organizes the magnetic field on a scale we rarely witness. This process might be so efficient that it suppresses the smaller scale, turbulent dynamo action that usually creates a more disorganized magnetic map. Yet there remains a possibility that we are witnessing the effects of something even more fundamental. The sheer strength and coherence of these fields might be a fossil relic, a preserved magnetic imprint from the galaxy's very formation. When the primordial cloud of gas that would become NGC 1300 first collapsed, the weak magnetic field present in the early universe would have been compressed and amplified, frozen into the resulting structure as it took shape. If this is the case, the organized fields we see today are not being actively generated by current processes, but are instead a living snapshot of the magnetic conditions that existed billions of years ago, a rare and well-preserved artifact from the galaxy's birth that has somehow managed to survive eons of chaotic evolution. This would make NGC 1300 a unique cosmic museum, allowing us to study the magnetic fields of the early universe directly. The implications of these anomalous fields extend far beyond mere curiosity, as they actively reshape the physical environment of the galaxy. A magnetic field of this strength and uniformity is not a passive observer, it is a powerful player. It can provide structural support against the force of gravity, preventing giant clouds of gas from collapsing to form new stars. This could be a key piece of the puzzle in explaining the strange, patchy star formation we discussed earlier, where some regions are bursting with new stars while others, rich with gas, remain mysteriously dormant. The magnetic field could be acting as a cosmic brake, holding those clouds in a state of suspended animation. Furthermore, these organized fields can influence the propagation of cosmic rays, high-energy particles shooting across the galaxy, and guide the flows of ionized gas, effectively directing the circulation of matter and energy along invisible magnetic highways. The discovery of such a powerful and structured magnetic force compels us to rewrite the models of how energy, matter, and fundamental forces interact within a grand spiral galaxy. revealing a layer of complexity we are only beginning to appreciate. This brings us to a central feature of the galaxy, one that defines its very identity yet holds a secret that challenges our timeline of cosmic evolution. The magnificent bar at the heart of NGC 1300 is its most striking characteristic, a straight, dense lane of stars and gas cutting through the galactic center from which the glorious spiral arms flow. According to our most sophisticated computer simulations, such bars are not permanent structures. They are dynamic, transient features born from gravitational instabilities within a galaxy's disk. These models suggest that once formed, a bar is a cosmic agitator. Its immense gravitational pull acts like a shepherd, violently funneling gas inward toward the central black hole, fueling immense activity. This very process, however, is the bar's undoing. The constant transfer of energy and angular momentum is predicted to make the bar unstable over time. Within a few billion years, it should naturally weaken, buckle, and ultimately dissolve back into the disk, perhaps to be reborn later in a cyclical dance of creation and destruction. But NGC 1300 bar defies this entire narrative. It doesn't show the signs of a young, chaotic structure. Instead, it presents itself as an ancient, settled, and remarkably stable feature. Its stars are predominantly old and yellow, indicating they formed in a single, early epoch rather than in continuous waves of bar-driven activity. The structure itself appears rigid and well-defined, lacking the telltale warps, curves, or boxy shapes that simulations predict should develop as a bar ages and becomes unstable. It's as if we've discovered a mighty river that, according to all hydrological models, should have meandered and changed its course millennia ago, yet it remains locked in its original path, flowing with an unchanging and impossible permanence. This is the galactic bar paradox, a structure that behaves as if it is both billions of years old and yet shows no signs of the aging process our science expects. So what unseen force is acting as the cosmic glue, holding this giant structure together against its predicted fate? One compelling theory points to the very dark matter halo whose absence we previously questioned. While its overall distribution might be anomalous, it's possible that dark matter is playing a crucial role right here. A specially configured dark matter halo with a certain density and shape could provide a stabilizing gravitational influence. Imagine the bar is a spinning ruler. If you spin it in empty air, it will wobble and eventually break. But if you spin it within a thick, viscous fluid, the surrounding medium dampens those oscillations and keeps it stable. A precisely arranged dark matter halo could be acting as that viscous fluid, providing a background gravitational field that suppresses the instabilities that would otherwise tear the bar apart over cosmic time. Another fascinating possibility lies in the bar's own structure. Perhaps it is not a simple, solid rod of stars. It might harbor a dense central core or a specific mass distribution that makes it inherently more stable, a perfect architectural balance that our current models haven't yet stumbled upon. Its very formation history could be the key. If NGC 1300 formed from an unusually quiet and monolithic collapse of gas, rather than through the violent mergers that disrupt galactic disks, its bar might have formed early and gently, locking into a stable configuration from the very beginning that has persisted ever since. The implications of this stability are profound. It suggests that our understanding of how galaxies evolve internally is still in its infancy. We may be missing fundamental physics in our simulations, perhaps related to the complex interplay between stars, gas, dark matter, and magnetic fields. This ancient bar isn't just a beautiful feature, it's a living fossil. By studying its precise structure, the motions of its stars, and its gravitational influence, we are essentially reading a history book that records the conditions of the early universe. Its continued existence forces us to rewrite the life story of barred spiral galaxies, painting a picture where some structures, once formed, can achieve a graceful and permanent maturity, presiding over their galactic domains for nearly the entire age of the universe. While the organized magnetic fields shape the galaxy's structure, another form of energy reveals a hidden layer of violent and enigmatic activity. Peering into NGC 1300 with X-ray telescopes unveils a sky ablaze with brilliant, pinpoint sources of high-energy radiation. These are not the faint, diffuse glow of hot gas, but intense, localized beacons that signal some of the most extreme environments in the universe. While many of these can be explained as X-ray binary systems, where a black hole or neutron star is actively devouring material from a companion star, a significant number remain stubbornly unidentified. They are brilliant mysteries shining with the power of millions of suns, yet they don't correspond to any known type of X-ray binary, and they are far removed from the galaxy's quiet core, ruling out activity from the central supermassive black hole. Their very presence and peculiar properties suggest we are looking at a population of objects that defy our current catalog of celestial phenomena. The nature of these mysterious X-ray emitters is a subject of intense debate, with several compelling theories vying for explanation. One leading hypothesis points to the existence of a hidden population of intermediate mass black holes. We are familiar with stellar mass black holes, formed from collapsing stars and weighing up to several dozen times the mass of our Sun. And we know of the supermassive giants that lurk in galactic centers, weighing millions or billions of solar masses. But the intermediate category, ranging from hundreds to hundreds of thousands of solar masses, has been notoriously elusive. These unidentified X-ray sources could be just that missing link black holes, perhaps the stripped-down cores of devoured dwarf galaxies or the ancient seeds from which supermassive black holes grew. If one of these intermediate black holes were to capture and begin consuming a nearby star, the resulting accretion disk would shine brightly in X-rays, creating exactly the kind of powerful, isolated source we detect. Another fascinating possibility is that we are witnessing the signature of exotic stellar remnants behaving in unprecedented ways. This could include a type of ultra-luminous X-ray source, or ULX, whose observed brightness pushes against the theoretical limit for how intensely a standard stellar mass black hole can accrete matter. Some scientists propose that these particular ULXs might be standard black holes whose light is being beamed directly toward us by a thick, rotating disk of material, like a cosmic lighthouse focusing its beam in our direction. Alternatively, they could involve a new class of object, such as a magnetar with an even more powerful magnetic field than any we've yet documented, capable of channeling incredible energies into X-ray emissions. Perhaps the most intriguing explanation involves not a single object, but a rare and catastrophic event. Some of these sources could be the aftermath of a hypernova, an exceptionally powerful stellar explosion that leaves behind a rapidly spinning magnetar and a long-lasting echo of high-energy radiation. Others might be the brilliant, lingering remnants of a neutron star collision, a kilonova, which forges heavy elements like gold and platinum, and can leave behind a short-lived, incredibly dense object that radiates intensely in X-rays as it cools and settles. The fact that these sources are scattered throughout the galaxy's disk and not concentrated in its star-forming arms adds to the puzzle, suggesting that the triggers for these events are not solely tied to the areas of most active stellar birth. Each unidentified source is a story waiting to be read, a clue to a more diverse and violent cosmic ecosystem than we ever imagined. Tucked away in the vast outer reaches of NGC 1300, far beyond its brilliant spiral arms, lies a reservoir of potential that stubbornly refuses to realize its purpose. Radio telescope surveys have mapped enormous, massive clouds of neutral hydrogen gas-cold, primordial material that is the essential building block for new stars. These are not small, wispy tendrils. These are colossal structures, some containing enough raw material to form millions of suns. In any typical galactic environment, clouds of this immense size and density would be the sites of furious stellar birth, glowing with the fierce blue light of infant stars and the pink blush of ionized hydrogen. Yet here they remain eerily dark and silent. This profound inactivity is the central mystery. Why would a galaxy seemingly hoard such immense wealth of star-forming fuel and then leave it sitting idle, untouched and unused? The investigation into this cosmic paradox leads us to the delicate physics of star formation itself. For a gas cloud to collapse and ignite new stars, a precise set of conditions must be met. The inward pull of gravity must overcome all outward pressures that support the cloud, primarily thermal pressure, the heat of the gas itself, and turbulent motion. It appears that within these dark hydrogen clouds, something is actively propping the gas up, preventing gravity from winning the battle. One of the prime suspects is an unexpected lack of the very triggers that normally kick-start this process. In the bustling spiral arms of a galaxy, star formation is often initiated by external shocks. These can be the density waves that create the arms themselves, the blast waves from nearby supernova explosions, or the gravitational nudges from passing star clusters. These events compress the gas, creating dense knots where gravity can finally take hold. But these vast outer clouds exist in a state of profound isolation, floating in the galactic hinterlands where such triggering events are exceedingly rare. Without a catalyst to push them over the edge, they simply linger in a stable but sterile state of equilibrium. However, the absence of a trigger may not be the only force at work. There could be an active inhibitor maintaining this cosmic stalemate. This is where the galaxy's mysterious and powerful magnetic fields, which we've discussed before, may play a decisive role. If these magnetic field lines permeate these outer clouds with the same strength and organization we see elsewhere, they could be providing a formidable supporting force. Imagine the gas cloud is filled with an invisible web-like structure. The magnetic fields act like an array of incredibly fine, super-strong springs that counteract the force of gravity, preventing the cloud from compressing enough to form the dense cores that become stars. In this scenario, the gas is effectively caged by magnetism, held in a state of suspended animation that could last for billions of years. Another fascinating possibility involves the temperature and chemistry of the clouds themselves. To collapse, the gas must be able to cool down, radiating away its thermal energy. This cooling is typically done through molecules like hydrogen, which form on the surface of microscopic dust grains that act like tiny radiators. If these particular clouds are somehow deficient in these dust grains, perhaps because they are composed of primordial gas that has never been enriched by the elements forged inside previous generations of stars, their ability to cool efficiently would be severely hampered. They would remain just a little too warm and too energetic for their own gravity to pull them together. They are not just dark, but also too hot to make stars, a frustrating paradox for a cloud of cold gas. The existence of these dormant giants forces us to reconsider the entire life cycle of a galaxy. We typically think of galaxies as either actively forming stars or as dead and red, having exhausted their fuel. NGC 1300 presents a third, more nuanced state, a galaxy that is actively choosing not to form stars in its outer regions, effectively banking an immense amount of fuel for its future. This hoarded reservoir could be a long-term survival strategy. When the galaxy eventually consumes the gas in its inner disk, it could tap into this vast external savings account, triggering a new wave of star formation that would rejuvenate it billions of years from now. These dark hydrogen clouds are not a sign of a dying galaxy, but potentially the key to its very long-term survival, a secret stash of cosmic potential waiting for its moment to shine. Now we turn from the grand forces of gravity and magnetism to the very elements that make up the galaxy. And here we find a distribution of matter so strange it rewrites the story of cosmic enrichment. Across the vast expanse of NGC 1300, astronomers have been diligently reading the chemical signatures of its stars and gas clouds, and the results are deeply puzzling. The galaxy is a bizarre chemical mosaic, a patchwork where regions of extreme elemental sophistication lie immediately adjacent to zones that are chemically primitive, almost untouched by the alchemy of stellar life and death. In one sector, you might find stars and nebulae incredibly rich in rare, heavy elements like europium, gold, and platinum metals that can only be forged in the most violent stellar explosions. Just a short cosmic distance away, another region appears anemic, composed almost entirely of the primordial hydrogen and helium that existed just after the Big Bang, with a shocking absence of these heavier elements. This wild, unpredictable variation defies the standard model of galactic chemical evolution, which predicts a much more gradual and uniform enrichment process as a galaxy ages. This standard model is a beautiful and logical story. A galaxy starts its life with a pristine cloud of hydrogen and helium. The first generation of massive stars ignites, lives its brief, furious life, and then explodes as supernova, seeding the surrounding gas with the first heavy elements carbon, oxygen, iron. The next generation of stars forms from this now enriched gas, lives, dies, and contributes an even richer mix of elements. Over billions of years, through countless cycles of stellar birth and death, the entire galaxy should become progressively more chemically complex in a relatively even, homogenized way. The sheer force of supernova blasts and stellar winds should act like a giant cosmic mixer, stirring these newly forged elements throughout the galactic disk. But NGC 1300 clearly didn't get the memo. Its chaotic chemical map suggests this mixing process has been strangely inefficient or repeatedly reset in certain areas, leaving behind a fossil record of isolated events rather than a smooth, galaxy-wide progression. So what could cause such a stark and localized imbalance? One compelling theory brings us back to the galaxy's majestic bar. This massive structure is not just a visual feature, it's a powerful engine that dictates the flow of matter. The bar's relentless gravitational pull is incredibly efficient at funneling gas inward from the outer disk. This means that fresh, chemically primitive gas that has never been involved in star formation, is constantly being siphoned from the galactic outskirts and delivered directly to the inner regions. This influx of pristine fuel could effectively dilute the chemical enrichment in the inner disk, washing out the concentration of heavy elements and creating those puzzling pockets of primordial chemistry right next to the sites of the most recent and violent stellar activity. The bar acts as a delivery system for youth, constantly injecting a supply of virgin material into the heart of the galaxy. On the other end of the spectrum, the surprising pockets of extreme enrichment point to a different kind of history. These regions, blazing with the signature of rare heavy elements, are likely the sites of recent and incredibly specific types of cataclysms. Elements like gold and platinum are not created in the common supernova of massive stars. They are believed to be forged almost exclusively in the collisions of ultra-dense stellar remnants neutron stars. The presence of these elements in high concentration suggests that a neutron star merger occurred relatively recently in that specific location, seeding that immediate neighborhood with its unique metallic bounty before the ejected material could be scattered and diluted by the general galactic turbulence. The chaotic flow patterns driven by the bar might then isolate these enriched pockets, preventing them from spreading and instead leaving them as chemical hotspots, like concentrated spices that haven't been stirred into the galactic soup. This bizarre chemical landscape turns NGC 1300 into a unique laboratory for studying the life cycles of elements. It provides direct evidence that a galaxy's chemical evolution is not a single, unified story, but a collection of thousands of local histories. Some areas have been roiled by frequent stellar deaths, becoming cosmic crucibles of complexity. Others have been relatively quiet, preserving a glimpse of the ancient universe. And still others have been flooded with fresh gas, resetting their chemical clock. This patchwork challenges the very idea of a galaxy's age, showing us that within a single structure, you can find regions that are chemically ancient, adolescent, and newborn, all existing simultaneously under the same swirling canopy of stars. This brings us to a feature of NGC 1300 that is both its most visually stunning characteristic and one of its most profound physical puzzles: its breathtaking and near-perfect symmetry. In a universe governed by chaos, where collisions, mergers, and turbulent forces constantly reshape galaxies into lopsided and irregular forms, NGC 1300 stands as a majestic outlier. Its two principal spiral arms unwind from the ends of its central bar in a flawlessly mirrored, bisymmetric pattern that would satisfy even the most rigid mathematician. This isn't just a rough resemblance. The arms are almost exact copies of each other in their curvature, pitch, and the spacing of their star-forming knots. Such precise order emerging from the inherently violent and stochastic process of galaxy formation is like finding a perfectly polished diamond in the middle of a landslide. It defies all expectations of cosmic disorder and points to the presence of a hidden, organizing hand. The existence of this symmetry is a direct challenge to our standard models of spiral structure. The prevailing theory for many spiral galaxies is the density wave theory, which posits that spiral arms are not permanent structures but are like traffic jams in a stream of stars and gas, caused by a rotating gravitational wave that moves through the galactic disk. While this theory explains why arms can persist for billions of years without winding up too tightly, it does not naturally produce the kind of perfect two-armed symmetry we see here. Density waves are notoriously messy. They often produce ragged, multi-armed or lopsided patterns as they interact with the chaotic distribution of mass in a galaxy. The flawless mirroring in NGC 1300 suggests that its spiral structure is not a transient wave but something far more fundamental and stable, perhaps permanently etched into the very fabric of the galaxy's gravitational field. So what unseen force could be acting as the cosmic architect, sculpting this perfect order from chaos? The prime suspect is without a doubt the galaxy's massive bar. This central structure is not a passive feature, it is the galaxy's dominant gravitational engine. Computer simulations show that a strong, stable bar can effectively organize an entire disk, orchestrating the motion of stars and gas into a coherent, symmetrical pattern. As the bar rotates, it creates resonant orbit-specific paths where stars and gas clouds complete their orbits in sync with the bar's rotation. These resonances can effectively trap material, forcing it into a beautifully ordered, two-armed spiral structure that is a direct extension of the bar itself. In this scenario, the bar acts like a master conductor, and the spiral arms are the orchestra, playing a perfectly synchronized symphony of motion dictated by the gravitational baton. However, this explanation only deepens the mystery because it circles back to the earlier paradox of the bar's own impossible stability. For the bar to maintain this perfect symmetry for billions of years, it must itself be incredibly rigid and unchanging, immune to the instabilities that should theoretically cause it to buckle or dissolve. This suggests that the symmetry we admire is not just skin deep. It is a symptom of a galaxy that exists in a state of profound gravitational equilibrium. Every component, from the dark matter halo to the distribution of stars, must be perfectly balanced to support this enduring order. The symmetry is therefore a clue, a visible signpost pointing toward the hidden physics, be it a unique dark matter distribution, a specific magnetic field configuration, or an unusually quiet formation history that has allowed NGC 1300 to achieve this state of graceful, permanent maturity. Its beautiful arms are not just a pretty picture, they are the outer expression of an inner cosmic harmony that we are only beginning to comprehend. Yet even this intricate dance of light and shadow may not be the final explanation, as these echoes have revealed a second, even more profound possibility. The precise timing and subtle warping of some light echoes don't perfectly align with the expected reflection of simple dust clouds. Instead, their patterns suggest that the path of the supernova's light itself is being bent by an immense gravitational field, a phenomenon predicted by Einstein's general relativity. This means that some of what we're calling a light echo could actually be the ghostly signature of warped spacetime around a massive, hidden object. The incredible burst of light from the exploding star is acting like a single, brilliant flash from a cosmic camera, and as it passes through regions of distorted space, its path is curved, creating delayed and distorted images that reach us long after the main event. We are potentially seeing the lensing effect of a previously unknown intermediate mass black hole or a dense, dark matter subhalo drifting through the galactic disk, its immense gravity revealed only by the temporary passage of this brilliant flash. This turns the light echo from a simple illuminator of dust into a direct probe for some of the most elusive and massive objects in the galaxy, objects that have otherwise left no trace on our telescopes. The implications of these ghostly echoes extend far beyond a single supernova event. They provide a powerful, transient tool for mapping the invisible architecture of the entire galaxy. Each detected echo is like a sonar ping sent through the cosmos, revealing the contours of hidden structures we could never see directly. By carefully timing the arrival of these echoes and analyzing their spectra, astronomers can construct a three-dimensional map of the intervening dust clouds, determining their composition, density, and distance from the supernova with incredible precision. Furthermore, if gravitational lensing is indeed at play, these events offer a rare chance to weigh and locate dark, massive objects that would otherwise be completely invisible to us, providing crucial data for our understanding of dark matter's distribution. These faint reverberations of light are therefore more than just a cosmic curiosity. They are a sophisticated diagnostic tool, allowing us to perform a kind of non-invasive surgery on the galaxy, revealing its hidden anatomy through the careful study of echoes from a stellar death. Now we encounter a void on a truly cosmic scale, one that surrounds the galaxy itself. According to our most successful cosmological models, a majestic spiral like NGC 1300 should be the gravitational anchor for a bustling system of smaller satellite galaxies. These dwarf galaxies, each containing millions or billions of stars, are the cosmic equivalent of moons orbiting a planet, and they are considered a fundamental prediction of the cold, dark matter model of the universe. The theory states that large galaxies form within immense halos of dark matter, and the gravitational clumping of this invisible substance naturally attracts smaller subhalos, which themselves should host these visible dwarf satellites. Yet when astronomers search the space around NGC 1300, they find a startlingly sparse neighborhood. The number of observed satellite galaxies is far fewer than what the simulations predict, creating a significant gap between theory and observation that forces us to question our understanding of how cosmic structures assemble. This missing satellite problem isn't unique to NGC 1300, but its severity here is particularly pronounced. Several compelling theories attempt to explain where these galaxies might have gone. The most straightforward possibility is a history of cosmic carnage. NGC 1300, with its immense gravitational pull, could be a galactic cannibal. Over billions of years, it may have already consumed the vast majority of its original satellite family, tearing them apart with tidal forces and assimilating their stars into its own halo and outer disk. The evidence for this might be the very streams of counter-rotating gas we discussed earlier, the final, dissolving remnants of these long-devoured companions. In this scenario, the missing satellites aren't missing at all. We are simply seeing them in a different, more assimilated form, their identity erased by the relentless appetite of their giant host. A more subtle explanation involves not destruction but invisibility. It's possible that the dark matter subhalos are still there, orbiting the galaxy just as the models predict, but they failed to form many or even any stars. These would be known as dark galaxies, halos of dark matter with little to no visible matter to mark their presence. This could happen if the primordial gas that was pulled into these small halos was too effectively heated by the early ultraviolet background radiation from the first stars and galaxies, preventing it from cooling and collapsing to form stars. Alternatively, feedback from an early population of supernova in these tiny galaxies could have blown out all of their gas, shutting down star formation almost before it began and leaving behind only a dark matter ghost. Our telescopes, which see by starlight, would look directly through them, completely unaware of their massive, silent presence. This mystery also invites us to reconsider the fundamental properties of dark matter itself. Perhaps the particles that make up this mysterious substance are not completely cold and collisionless, as in the standard model. If dark matter has even a slight tendency to interact with itself, a property known as self-interacting dark matter, these interactions could effectively smooth out the smaller subhalos, preventing them from ever reaching the densities needed to attract and hold onto the normal matter that forms stars and galaxies. The dark matter halo of NGC 1300 would then be quieter and smoother, lacking the numerous smaller clumps that should host visible satellites. The galaxy's unusual quietness and stability, from its ancient bar to its missing dark matter signature, could all be facets of the same underlying puzzle, pointing toward a more complex and interactive nature for the universe's most dominant yet elusive substance. Yet, even as we map the grand movement of the galaxy itself, a closer look at individual stars reveals a chaotic undercurrent beneath the ordered spiral. While the vast majority of stars in NGC 1300 obediently follow the flow of galactic rotation, tracing graceful, predictable arcs around the galactic center, a small but significant number are outright rebels. These stars exhibit anomalous proper motions, meaning they are moving in completely unexpected directions or at peculiar speeds that defy the gravitational choreography of the entire galaxy. It's the difference between watching a school of fish all swimming together in a coordinated current and suddenly spotting a few individuals darting off at sharp angles or racing ahead of the pack for no apparent reason. These stellar mavericks present a direct challenge to our gravitational models, forcing us to ask what invisible hand is giving them a push or a pull that we cannot directly see. The immediate suspicion falls on the usual gravitational suspects within the galaxy. The most straightforward explanation could be the lingering effects of a recent minor merger. If a small dwarf galaxy or a massive globular cluster was recently consumed by NGC 1300, the stars it donated would not immediately settle into the common rotation. They would retain the unique velocity and direction of their original parent object, creating streams of stars moving on similar, peculiar paths. These stellar streams would be the cosmic equivalent of seeing a group of people walking against the crowd in a train station, all heading in the same unusual direction because they just got off a different train. The challenge is that such streams are often faint and difficult to detect against the brilliant backdrop of the galaxy's own stars, requiring incredibly precise measurements to uncover. However, the erratic motion of isolated stars points to a more dynamic and ongoing process. A star could receive a massive gravitational kick from a close encounter with a much more massive object. Imagine a single star wandering too close to a dense, unseen cluster of stellar mass black holes. The immense gravitational slingshot effect from such an encounter could eject it from its original orbit, sending it speeding across the galaxy on a new, highly eccentric path. Similarly, a near miss with another star in a densely populated region could act like a gravitational billiard shot, altering its course in a way that seems random and inexplicable when we only see the outcome millions of years later. The galaxy, for all its apparent order, is a vast playground of gravitational interactions, and these stellar rebels are the living evidence of its violent and unpredictable nature. Perhaps the most intriguing possibility involves the hidden architecture of the galaxy's dark matter halo. If this halo is not the smooth, symmetrical sphere that most models assume, but is instead lumpy and asymmetrical with dense substructures, then its gravitational influence would be uneven. A star passing through a particularly dense knot of dark matter would experience a slight but significant gravitational tug, a perturbation that could subtly alter its orbit over millions of years. We wouldn't see the knot itself, but we would see its effect on the star's motion, a ghostly hand gently nudging a star off its expected course. This would make these anomalous stars not just puzzles to be solved, but potential tracers, whose strange paths could actually help us map the invisible and mysterious dark matter distribution within the galaxy, using their light to illuminate the darkness that guides them. Rising high above and plunging deep below the luminous disk of NGC 1300, astronomers have discovered a pair of colossal, ghostly structures that defy easy explanation. These are the radio bubble structures, vast balloons of invisible energy that dwarf the entire visible galaxy, stretching for tens of thousands of light years into the otherwise empty galactic halo. We cannot see them with optical telescopes. They reveal themselves only through the faint hiss of synchrotron radiation, a type of emission generated by electrons spiraling at near light speed around magnetic field lines. The existence of such Fermi bubbles is not entirely unique. Our own Milky Way has them, but their presence around a galaxy with such a mysteriously quiet core makes them a profound paradox. These bubbles are the undeniable signature of a past eruption of unimaginable energy, a titanic burp from the galaxy that must have occurred sometime in the last few million years. The central mystery is that we can find no obvious culprit for this cataclysm in the galaxy's recent history. It's as if we discovered the crater of a massive explosion but found no trace of the bomb that could have caused it. The physics behind these structures points to an event of almost inconceivable power. To inflate bubbles of this size and keep them energized against the pressure of the surrounding intergalactic medium requires a sustained injection of energy, likely from a relativistic jet, a narrow beam of particles and magnetic fields shooting out at nearly the speed of light. This is the kind of activity exclusively associated with a feeding supermassive black hole in its active quasar phase. The jet would have acted like a cosmic blowtorch, pumping energy into the galaxy's halo for millions of years, creating a vast cavity that is now filled with these fast-moving particles and magnetic fields. The fact that the bubbles are still visible, still emitting radio waves, means this event happened relatively recently on a cosmic timescale. Otherwise, they would have dissipated and faded from view. Yet, when we look at the core of NGC 1300 today, we see only that silent, dormant giant. There is no jet, no sign of recent violent activity, and no visible evidence in the optical spectrum of such a recent galaxy-shaking event. This forces us to confront a startling possibility that the most energetic episode in this galaxy's recent history was both incredibly violent and astonishingly brief, leaving behind these giant ghostly bubbles as the only monument to its occurrence. So what could have caused such a powerful yet seemingly transient explosion? One compelling theory brings us back to the galaxy's quiet black hole and its potential for brief, violent feasts. While it appears dormant now, it may have experienced a sudden and spectacular meal. The prime suspect is a massive star or a large gas cloud that strayed too close and was torn apart in a tidal disruption event. However, the energy required to inflate these bubbles is far greater than a single star could provide. A more likely feast would have been an entire globular cluster, one of those missing ancient star clusters we discussed earlier, dragged into the center by dynamical friction. The sudden, catastrophic ingestion of hundreds of thousands of stars at once could have provided the immense fuel load needed to power a short-lived but incredibly violent quasar phase, unleashing a jet that inflated the bubbles before the black hole consumed all the fuel and returned to its dormant state. This would have been a brief, spectacular flash of activity in the galactic core, a fireworks display that ended as suddenly as it began. Another fascinating possibility involves the collective power of starburst activity, though this is a less likely candidate. If a wave of star formation in the central regions produced an unprecedented number of supernovae in a short period, the combined force of their winds and radiation could theoretically drive a massive outflow. However, for bubbles of this scale and specific radio signature, the energy would need to be focused and jet-like, which is not typical for starburst winds. The bipolar nature of the bubbles, their symmetry above and below the galactic plane, strongly suggests a focused ejection from the very center, the exclusive domain of the supermassive black hole. The presence of these radio bubbles is more than just a clue to a past event. It actively shapes the galaxy's current environment. These structures act as a containing vessel for cosmic rays, trapping high-energy particles within their magnetic confines and preventing them from escaping into the wider intergalactic medium. This could have a significant impact on the potential for star formation in the galaxy's outer disk by regulating the pressure and energy of the surrounding halo gas. They stand as a permanent reminder that a galaxy's present calm can be deeply deceptive, hiding a violent and energetic history written in faint radio waves across the cosmos, a history we are only just beginning to learn how to read. While the radio bubbles speak to a galaxy-scale explosion, a more subtle but equally puzzling phenomenon is occurring between the stars themselves, one that warps the very fabric of space to create fleeting cosmic mirages. Throughout NGC 1300, astronomers have documented a surprising number of gravitational microlensing events. This incredible effect occurs when a massive, compact object like a star, a black hole, or even a planet passes directly between us and a more distant background star. The invisible object's gravity acts like a tiny lens, bending and focusing the background star's light, causing it to temporarily brighten in a very specific, predictable pattern. These events are incredibly useful for finding dark, isolated objects that emit no light of their own. But in NGC 1300, the numbers simply don't add up. The frequency of these microlensing events is far higher than the known population of stars, white dwarfs, and neutron stars can possibly account for. It's as if we're walking through a familiar forest and constantly seeing the telltale flashes of sunlight being focused by lenses that aren't there, hinting at a hidden population of objects we cannot see. This surplus of invisible lenses forces astronomers to consider the existence of a vast number of dark, compact objects drifting silently between the stars. One leading candidate is a population of stellar mass black holes that far exceeds our predictions. When very massive stars die, they collapse into black holes, and it's possible that the early history of NGC 1300 was dominated by a generation of giant stars that left behind an unusually large number of these dark remnants. These black holes would now be scattered throughout the galaxy, completely invisible unless they were actively feeding or, as in this case, briefly lensing the light of a star far behind them. Their sheer numbers would suggest a fundamentally different initial recipe for star formation in this galaxy, one that favored the birth of behemoths that lived fast, died young, and left behind a galaxy filled with their dark ghosts. Another fascinating possibility involves objects that are not just dark but inherently exotic. Some scientists have speculated that a portion of the galaxy's dark matter could be locked up in massive, compact halos of it, or macho. This was a once popular theory suggesting that dark matter might not be a sea of invisible particles, but instead a multitude of ordinary objects that are simply too dim to see, like failed stars known as brown dwarfs or ancient cold white dwarfs. While this theory fell out of favor for explaining the majority of dark matter in the universe, the peculiar microlensing results in NGC 1300 could indicate that such objects are unusually abundant here, forming a significant component of the mass lurking between its bright stars. Yet the most intriguing explanations venture into the truly unknown. Could these lensing events be the signature of something even more exotic, like primordial black holes? These are hypothetical black holes that are not born from dying stars, but are thought to have formed from ultra-dense fluctuations in the hot, early universe. Ranging in mass from less than an asteroid to more than a star, they could be scattered throughout space, and a galaxy like NGC 1300 might have captured a great number of them within its immense gravitational well. Their detection through microlensing would be a monumental discovery, potentially solving several cosmic mysteries at once. Furthermore, the precise characteristics of some lensing events, their duration, the symmetry of the brightening, don't perfectly fit the profile of a single, solid object. This has led to more speculative ideas, such as the lensing effect being caused by dense clumps of dark matter particles or other, even more theoretical entities that we have yet to describe. Each unexplained flicker of a background star is a potential clue, a brief signal from the dark, unseen majority of the galaxy's mass, compelling us to map a universe that is far stranger and more densely populated with mysteries than we ever imagined. This unexpected flatness presents a profound challenge to the standard model of cosmology known as lambda cold dark matter. In this model, dark matter is cold, meaning its particles move relatively slowly, and it is collisionless, meaning these particles rarely, if ever, interact with each other or with normal matter except through gravity. Under these rules, dark matter halos should be roughly spherical with perhaps a slight elongation. They form through a process known as hierarchical clustering, where smaller clumps merge to form larger ones in a relatively chaotic manner, naturally producing a roundish, puffy distribution of dark matter around galaxies. The starkly flattened, disk-like halo of NGC 1300 suggests that this simple, elegant model might be missing a crucial piece of physics when applied to the complex environment of a massive barred spiral. Scientists are actively investigating several compelling theories to explain this bizarre geometry. One leading idea is that dark matter might not be completely collisionless after all. What if dark matter particles can interact with each other through some unknown force, a possibility known as self-interacting dark matter, or SIDM? In this scenario, as the dark matter particles swirl within the halo, these self-interactions would generate a form of friction. This friction would cause the particles to lose energy and settle into a more ordered, disk-like configuration, much like how the normal matter in a galaxy settled into a flat spiral disk. The immense gravitational influence of NGC 1300's massive and stable bar could have further sculpted this responsive dark matter, pulling and shearing it into its current oblate shape over billions of years. The galaxy's dark halo, in this view, isn't a static backdrop. It's a dynamic structure that has been shaped by the same galactic forces that organized its stars. A second, more radical line of thought questions not the nature of dark matter, but the very law of gravity itself. The flat halo is inferred from its gravitational effects, specifically the motions of stars and gas that indicate more mass must be present in a certain distribution. But what if our understanding of how gravity works on the colossal scale of a galaxy is incomplete? Alternative theories, most notably modified Newtonian dynamics or MOND, propose that gravity behaves differently when its pull becomes incredibly weak, as it does in the outskirts of galaxies. MOND suggests that we don't need any dark matter at all. The observed motions can be explained by a modification of the gravitational force. Intriguingly, some versions of MOND naturally predict a gravitational field that would appear to us as a flattened halo of phantom dark matter in a galaxy like NGC 1300. In this case, the halo's shape isn't a clue about invisible particles, but a direct signature of a fundamental rewrite of Einstein's and Newton's laws. The implications of this anomaly extend far beyond a single galaxy's peculiarity. If the dark matter halo is indeed flatter due to self-interactions, it means dark matter is not the simple, inert substance we've long assumed. It would have a rich and complex physics of its own, opening up a whole new field of study into the properties and behaviors of the universe's most abundant yet elusive material. If, on the other hand, the solution points toward modified gravity, it would constitute one of the most significant scientific revolutions in history, forcing us to rethink the fundamental force that literally holds the cosmos together. NGC 1300, with its precisely measured and strangely flattened gravitational field, has become a critical testing ground for these competing theories of the universe. Its unique structure offers a rare and powerful constraint, challenging cosmologists to build models that can account for this cosmic outlier, and in doing so, perhaps finally revealing the true nature of the dark universe. But the galaxy's capacity for surprise seems endless, as we now find ourselves investigating a mystery written in a specific, high-energy light that shouldn't be there. In certain regions of NGC 1300, space telescopes tuned to the ultraviolet part of the spectrum have detected a persistent and puzzling glow. Ultraviolet light is the signature of extremely high temperatures and immense energy, the kind typically radiated by the universe's most youthful and volatile stellar residents, massive, blue-white stars that burn furiously and die young. The strange part is that this UV excess isn't emanating from the galaxy's known stellar nurseries or its clusters of young, hot stars. Instead, it seems to bloom from seemingly quiet, older regions of the disk, places populated by cooler, older stars that should be glowing with a gentle red or yellow light, not a fierce ultraviolet radiance. It's as if we pointed a thermal camera at a forest at night and found patches of ground glowing with intense heat, yet when we look with our own eyes, we see only cool, damp soil and old trees, with no fire, volcano, or engine in sight to explain the warmth. This inexplicable glow forces astronomers to consider that what we see in visible light might be only a fraction of the story. One compelling line of investigation points to a hidden population of stars that have, for one reason or another, evaded our senses. The culprit could be a vast number of hot, faint stellar remnants known as white dwarfs. These are the exposed, Earth-sized cores of dead sun-like stars, and they can shine with a fierce ultraviolet light as they slowly cool down over billions of years. If a past wave of star formation in these apparently quiet regions was particularly prolific, it could have left behind a dense population of these ancient embers, whose collective ultraviolet output might account for the mysterious glow. Alternatively, we could be seeing the light from the sizzling accretion disks of binary systems where one white dwarf is actively siphoning material from a companion star, a process that heats the stolen gas to temperatures that blaze in the UV. Yet another fascinating possibility lies with a specific and violent phase at the end of a star's life. When a sun-like star exhausts its nuclear fuel, it doesn't go out with a supernova bang, but instead expels its outer layers in a beautiful, expanding shell of gas called a planetary nebula. At the heart of this glowing cloud lies the newly born white dwarf, and for a brief cosmic moment, a mere tens of thousands of years, the nebula itself is heated by the intense UV radiation from its central star, shining brilliantly in that part of the spectrum. If the rate of stellar death in these regions is just right, there could always be a handful of these short-lived planetary nebulae visible at any time, their combined light creating a steady, diffuse UV excess that lingers long after the individual nebulae have faded from view. However, some scientists argue that stellar sources alone may not be sufficient to explain the intensity and distribution of this glow, leading to more exotic and speculative theories. Perhaps we are witnessing the energetic signature of unknown high-energy processes occurring in the vast voids between the stars. The interstellar medium is not a perfect vacuum. It is threaded with magnetic fields and crisscrossed by cosmic rays, high-energy protons, and atomic nuclei accelerated to nearly the speed of light. The interaction of these cosmic rays with dense, cold clouds of hydrogen gas could potentially produce a diffuse ultraviolet fluorescence, a faint but pervasive light that would illuminate the galaxy's dark corners. Even more speculatively, some have proposed that the decay or annihilation of certain types of hypothetical dark matter particles could release energy in the form of ultraviolet photons. If true, this mysterious glow would be our first direct glimpse into the physics of the dark sector, a faint but telling signal from the universe's most secretive constituent. This ultraviolet excess is more than just a puzzling observation. It is a persistent question mark, challenging us to look deeper and consider that even the oldest, quietest parts of a galaxy can harbor untapped wells of energy and activity. Even as we map the grand, coherent flow of the galaxy's primary rotation, a closer inspection reveals a population of stellar rebels moving to the beat of a different drummer. Scattered throughout the halo and outer disk of NGC 1300 are stars that defy the galaxy's dominant spin, orbiting the core in a retrograde direction, backward against the prevailing current of billions of their neighbors. This phenomenon, known as counter-rotation, is a stark violation of the orderly motion we expect from a majestic spiral, and it serves as a powerful, lasting clue to a violent and disruptive chapter in the galaxy's distant past. The most compelling explanation for these stellar mavericks is a history of galactic cannibalism. Galaxies are not born in isolation. They grow over billions of years by gravitationally capturing and absorbing smaller satellite galaxies. The presence of these counter-rotating stars strongly suggests that NGC 1300 consumed a smaller dwarf galaxy that was itself orbiting in a retrograde path. As this ill-fated satellite was drawn in, its stars were stripped away by immense tidal forces, but they retained the momentum of their original orbit. Instead of being immediately assimilated into the galactic flow, these captured stars were left to travel on their rebellious paths, forming a fossilized record of that ancient collision. They are the celestial equivalent of finding a river with two powerful currents flowing in opposite directions. It's a clear sign that another body of water has recently merged with it, yet hasn't fully mixed in. However, the real mystery isn't just how these stars got here, but how they've managed to survive for so long without having their orbits erased. Within the dense, dynamic environment of a galactic disk, forces like dynamical friction and hydrodynamic drag should, in theory, work to quickly homogenize any such peculiar motions. The counter-rotating stars should constantly collide with the vast clouds of gas and other stars moving in the dominant direction, losing energy and momentum until they finally give in and join the main flow. The fact that we can still clearly detect these distinct populations means they have somehow avoided this fate for potentially billions of years. Their persistent defiance suggests they exist in relatively isolated pockets or specific orbital resonances, protected from the erasing effects of constant interaction. They are cosmic holdouts, preserving a memory of a violent event that would otherwise have been completely smoothed away by time. This opens up a fascinating line of galactic archaeology. By studying the chemical composition of these counter-rotating stars, astronomers can perform a detailed forensic analysis. Stars formed in different environments carry unique chemical signatures, specific ratios of elements like oxygen, magnesium, and europium that act as a birthplace fingerprint. If the counter-rotating stars show a distinctly different chemical pattern from the stars native to NGC 1300, it would be the smoking gun confirming their external origin. Furthermore, the specific mix of elements could tell us about the nature of the devoured dwarf galaxy itself, such as how many generations of stars it had lived through before the merger. painting a vivid picture of the victim in this cosmic encounter. The stability of these structures also provides critical data for testing the physics of the galactic environment. Their survival offers a unique natural experiment for measuring the viscosity and overall density of the interstellar medium in the galaxy's outskirts. If the gas is thinner and less turbulent than our models assume, it would explain how these counter-rotating stars can persist for eons without being assimilated. Each of these backward-orbiting stars is therefore more than just a celestial curiosity. It is a living fossil, a preserved piece of evidence that allows us to piece together the biography of a cosmic giant and understand the violent processes that have shaped it over billions of years. Now we turn from the light we can see to the invisible, high-energy particles that constantly bombard our planet, and here we find another profound discrepancy. Earth-based observatories and space telescopes designed to detect cosmic rays, high-speed protons, and atomic nuclei from deep space have recorded an unusually intense flux of these particles originating from the general direction of NGC 1300. Cosmic rays are a constant background drizzle from all across the sky, but this is more like a localized downpour, a persistent shower of high-energy particles that suggests a powerful and ongoing source within the galaxy. The mystery deepens when we try to pinpoint the origin of this energetic rain, as it doesn't seem to be coming from any of the usual suspects we'd expect to be cosmic ray factories. In a typical galaxy, the primary cosmic ray accelerators are the shock waves from supernova explosions. When a massive star dies, it blasts its outer layers into space at incredible speeds, creating an expanding shell of debris. The leading edge of this shell acts like a natural particle accelerator, a cosmic version of the Large Hadron Collider, capable of boosting protons and other atomic nuclei to nearly the speed of light. We should therefore see a strong correlation between the locations of known supernova remnants and the sources of cosmic rays. Yet, when astronomers overlay the map of this anomalous cosmic ray flux onto the optical image of NGC 1300, the hotspots don't align with the galaxy's recent supernova remnants or its most active star-forming regions. It's as if we're detecting the roar of a mighty engine, but when we look under the hood, we can't find the motor that's making all the noise. This forces scientists to consider that the galaxy might be hiding a population of dark supernova remnants. These would be the leftover shells of stars that exploded in the relatively empty galactic halo or within extremely dense, dark molecular clouds. In such environments, the expanding shockwave from the explosion would be invisible to our optical and even our X-ray telescopes, as there would be very little surrounding gas for it to illuminate. However, the shockwave itself would still be perfectly capable of accelerating particles to cosmic ray energies. We would be completely blind to the visual fireworks of the supernova, but we would still feel the invisible spray of high-energy particles it flung across space millions of years later. This would mean our historical record of stellar deaths in this galaxy is woefully incomplete, missing entire chapters written in a language of particles rather than light. An even more intriguing possibility points to the galaxy's central bar as the culprit, but not in a way we've seen before. The bar's immense gravitational field drives systematic and powerful shocks through the interstellar medium as it rotates. These large-scale shockwaves moving through the tenuous gas between the stars could themselves act as a colossal, galaxy-wide particle accelerator. Unlike the brief, violent shock of a single supernova, this would be a continuous, steady process, constantly re-energizing cosmic rays and explaining the persistent, high-level flux we detect. The bar would function less like a cannon and more like a massive conveyor belt, endlessly feeding particles into its acceleration mechanism. Then there are the more exotic theories that venture to the very frontiers of physics. Could we be seeing the indirect signature of dark matter? If the dark matter particles that supposedly make up the galaxy's halo are their own antiparticles, they might annihilate upon collision with each other. This process of matter-antimatter annihilation would release a tremendous amount of energy, producing a shower of standard model particles, including protons and antiprotons that would contribute to the cosmic ray flux we detect. The mysterious and uneven distribution of dark matter we've inferred in NGC 1300 could therefore be directly responsible for this anomalous particle rain. Alternatively, the source could be something even more unfamiliar, like a previously unknown type of energetic object, a massive, stable pulsar with an unprecedented magnetic field configuration, or a microquasar whose jet is pointed away from us, hiding its visible activity but not its particle output. Each of these cosmic rays arriving at our detectors is a messenger from a distant and energetic process, and their unexpected numbers are telling us that NGC 1300 is host to particle acceleration mechanisms of immense power that we have yet to fully discover or understand. Yet another perplexing layer to this cosmic void emerges when we consider the nature of the gas that should be there. The interstellar medium isn't a uniform fog, it's a complex multi-phase environment. There are vast clouds of cold, dense molecular hydrogen where stars are born, and there are warmer, more diffuse regions of atomic gas. In these strangely empty zones of NGC 1300, it appears that both phases are missing. This isn't a case where cold gas has simply been heated into a harder-to-detect state. It suggests a clearing mechanism powerful enough to sweep away all gaseous material, regardless of its density or temperature. This points toward a force that doesn't discriminate, a galactic-scale event that simply evacuated these regions entirely, leaving behind a true vacuum in a space that should be teeming with the raw stuff of creation. The mystery isn't just about missing gas, it's about the presence of a profound and seemingly unnatural emptiness. But the galaxy's catalogue of cosmic anomalies extends even to the precise ticking of its most reliable clocks, its population of pulsars. These rapidly spinning neutron stars are the universe's ultimate timekeepers, emitting beams of radiation that sweep across space with a regularity that can rival atomic clocks. By mapping their locations and timing their pulses across other spiral galaxies, astronomers have established a predictable pattern. Pulsars are typically concentrated in the dense stellar environments of the spiral arms and central bulge, with their spin rates or periods following a fairly standard distribution. In NGC 1300, however, this pattern completely unravels. The spatial distribution of these cosmic lighthouses is bizarrely uneven, and their spin characteristics are unlike anything documented elsewhere, suggesting that the rules governing the birth and life of neutron stars here are fundamentally different. The first glaring oddity is their location. Instead of being neatly tracing the galaxy's magnificent spiral arms, a significant number of pulsars are found scattered far out into the galactic halo, and even more puzzlingly, clustered in the apparently empty spaces between the arms. It's as if you were studying a major city and found that a large portion of its most precise clocks weren't in the bustling downtown or residential neighborhoods, but had been mysteriously relocated to the remote countryside and empty fields on the city's outskirts. This unusual placement immediately raises a critical question. How did these pulsars get there? Neutron stars are born in the supernova explosions of massive stars, and massive stars have very short lives, meaning they don't have time to wander far from their stellar nurseries before they die. Finding pulsars so far from current star-forming regions implies they received a tremendous kick at birth, a gravitational slingshot from an asymmetrical supernova explosion that launched them on a high-velocity journey across the galaxy. The sheer number of these runaway pulsars in NGC 1300 suggests that supernovae here are consistently more violent and off-kilter than anywhere else we've observed, imparting unusually high recoil velocities to their collapsing cores. Yet the mystery deepens when we examine the pulsars themselves, specifically their rotation. Pulsars are born spinning incredibly fast, often hundreds of times per second, and they gradually slow down over millions of years as they lose rotational energy. This creates a predictable relationship between a pulsar's age and its spin period. Younger pulsars spin faster, older ones slower. In NGC 1300, this relationship is completely scrambled. The galaxy hosts an overabundance of extremely slow, old pulsars with periods of several seconds, but it also contains a surprising number of middle-aged pulsars that are spinning much faster than they should be, as if they've somehow found a fresh source of energy to keep them wound up. This bizarre distribution of spin rates points to unusual and sustained influences acting on these dead stars long after their violent birth. Several compelling theories attempt to explain this chronological chaos. For the unexpectedly fast spinners, the explanation might lie in a ready supply of cosmic fuel. If these pulsars are in binary systems, they could be actively accreting or stealing material from a companion star. As this stolen gas spirals onto the neutron star, it transfers angular momentum, effectively spinning it back up like a top being constantly whipped. The strange distribution of gas throughout NGC 1300, with its hidden reservoirs and counter-rotating streams, could be providing the perfect environment for this process to occur more frequently than in other galaxies. For the preponderance of extremely slow pulsars, the answer might be found in the galaxy's powerful magnetic fields. A neutron star's magnetic field acts as a brake on its rotation, and if the magnetic fields in NGC 1300 are inherently stronger or configured in a way that enhances this braking effect, it could cause pulsars to spin down to a lethargic crawl much faster than normal, creating a population of cosmic timekeepers that seem prematurely aged. The most profound implication of these unusual pulsars is that they force us to reconsider the very life cycle of neutron stars. Their strange locations and spin rates suggest that the environment of a galaxy is not just a backdrop, it actively shapes the evolution of its stellar remnants. The specific dynamics of NGC 1300, from its bar-driven shocks to its anomalous magnetic fields, appear to be writing a unique evolutionary history for its dead stars, one that is recorded in the erratic ticking of these distant celestial clocks. By studying this aberrant population, we aren't just learning about pulsars, we are uncovering a new layer of galactic influence where the largest structures dictate the fate of the smallest, most dense objects within them. Now we come to a structural mystery hidden within the very fabric of the galaxy's gravitational field, one that presents a shape so unexpected it challenges our most fundamental ideas of how dark matter should behave. Detailed analyses of stellar motions and gravitational lensing effects within NGC 1300 have revealed evidence for a feature that sounds more like science fiction than established astrophysics, a vast, coherent ring of dark matter. This isn't a smooth, spherical halo, but a distinct toroidal structure, a cosmic donut suspected to be woven through the galaxy's outer disk. The gravitational data suggests that an immense amount of unseen mass is arranged in this specific, highly ordered configuration, a finding that is profoundly difficult to reconcile with our standard cosmological models. This proposed ring is not a subtle feature. Its gravitational signature implies a density and clarity that makes it stand out against the expected background haze of dark matter, like finding a single, perfectly tied knot in a ball of random yarn. The very existence of such a ring forces a radical rethinking of how dark matter behaves. In the prevailing lambda cold dark matter model, dark matter is cold, meaning its particles move slowly, and collisionless, meaning they pass through each other and normal matter without interacting, feeling only the pull of gravity. Under these rules, dark matter should simply collapse into a roughly spherical, featureless halo around a galaxy. It should not, and indeed cannot, naturally clump into such a sharp, organized ring without some additional physical process at work. The presence of this ring is a direct challenge to the collisionless assumption, strongly hinting that dark matter particles might actually interact with each other through some unknown force. If dark matter has even a slight tendency to interact, a property physicists call self-interacting dark matter, then friction between particles could allow them to settle into a stable, disk-like or ring-like structure, much like how normal matter settled into the galaxy's spiral disk. The ring would then be a permanent gravitational sculpture carved by forces we are only beginning to imagine. An alternative and equally revolutionary explanation does away with dark matter entirely and looks instead to a modification of the laws of gravity itself. Theories like modified Newtonian dynamics, or MND, propose that our understanding of gravity is incomplete on the scale of galaxies. MND suggests that the force of gravity does not weaken as quickly over large distances as Newton's and Einstein's laws predict. Intriguingly, the gravitational effects of a dark matter ring, the specific way it influences the rotation of stars and the bending of light, could be precisely mimicked by a modification of gravity's fundamental equations. In this view, the ring is not a structure of invisible particles but a phantom, a ghostly imprint in the data caused by our use of the wrong gravitational rulebook. The ring becomes less a thing and more a place, a region where the modified laws of gravity produce effects that we, clinging to Einstein's theory, mistakenly attribute to a concentrated mass of dark matter. But how could a ring of dark matter form in the first place? The most plausible natural mechanism involves the galaxy's massive bar. This central structure is a powerful gravitational engine, and as it rotates, it creates waves and resonances throughout the galactic disk. It's possible that these resonances could have gathered and corralled dark matter particles over billions of years, herding them into a specific orbital path and creating a stable ring structure. This process would be similar to how Saturn's rings are shaped and maintained by the gravitational resonances with its moons. If this is true, then the dark matter ring is not a static relic. It is a dynamic feature, actively maintained by the continuous gravitational influence of the bar, and its existence provides a stunning example of how the visible and dark components of a galaxy can interact and co-evolve in complex ways. The implications of this ring extend far beyond a single galaxy's oddity. If confirmed, it provides a unique and powerful laboratory for testing the nature of dark matter. By studying the ring's precise density, size, and stability, physicists could potentially measure the strength of the proposed self-interactions between dark matter particles, a parameter that has so far been completely unknown. It would transition dark matter from a hypothetical, passive substance to an active component of the universe with its own rich physics and behaviors. Furthermore, the ring's orientation and relationship to the visible bar could offer crucial clues about the initial conditions of the galaxy's formation and the role dark matter played in shaping its majestic structure. This mysterious ring is therefore more than just a curiosity. It is a potential key, a cosmic cipher that could unlock the secrets of the invisible majority of our universe and reveal whether we need new particles or new laws of physics to finally understand the cosmos. And so we arrive at our final and perhaps most humbling mystery, one that forces us to confront not just the physics of a distant galaxy, but our own place in the cosmos. After exploring 29 strange phenomena, from silent black holes to phantom rings of dark matter, we are left with a profound and echoing quiet where we might have expected the most compelling evidence of all, the unmistakable signature of another intelligence. This is the great silence of NGC 1300. Here we have a galaxy that is ancient, massive, and richly complex, with all the ingredients and time necessary for life to arise and technology to flourish. Yet, despite our most sensitive and comprehensive searches, not a single confirmed technosignature, no narrowband radio signals, no laser pulses, no evidence of megastructures or astroengineering has ever been detected from its 60 billion stars. In a universe that should be teeming with life, This particular island of stars offers only a vast and unnerving silence. This absence immediately brings the famous Fermi paradox crashing into focus. If the conditions for life are not unique to Earth, and if galaxies like NGC 1300 have had over 10 billion years for intelligent species to emerge and expand, then the space between its stars should be buzzing with communication. The sheer scale and age of the galaxy make the silence statistically puzzling, even unsettling. It suggests that there might be a powerful, universal filter that prevents life from reaching a technological stage, or if it does, from surviving long enough to make its presence known across the interstellar void. Perhaps the development of advanced technology inevitably leads to self-destruction through war or environmental collapse. Or maybe life is simply far rarer and more fragile than we optimistically assume, and the great silence is the default state of the universe, with Earth being a spectacularly rare exception. But before we conclude that the galaxy is truly empty, we must consider the possibility that our methods of searching are fundamentally inadequate, like trying to scan a modern city for evidence of life using only a telescope designed to detect campfire smoke. Our current search for technosignatures is overwhelmingly biased by our own human experience and our century-old technology. We primarily listen for narrow-band radio signals because that's a technology we developed and can imagine others using. But what if a civilization vastly older than ours has moved far beyond radio communication? They might use neutrino beams, gravity waves, or some other information medium we haven't even discovered yet to communicate, their signals completely invisible to our current array of telescopes. Their presence might be evident in other, more subtle ways we are only learning to look for, like an anomalous thermal signature from a Dyson swarm or the spectral shadow of artificial pollutants in a planet's atmosphere. Furthermore, our search assumes a desire to be found, a willingness to broadcast one's existence to the cosmos. This may be a deeply anthropocentric viewpoint. A truly advanced civilization might practice intentional cosmic radio silence for reasons of security, privacy, or energy efficiency, considering wide-band broadcasting to be recklessly primitive or dangerously naive. They could be everywhere, enmeshed within the natural workings of their star systems, their technology so advanced and seamlessly integrated that it is indistinguishable from the natural astrophysical phenomena we are already studying. The very anomalies we've explored in this video, the strange infrared glow, the peculiar magnetic fields, the missing globular clusters, could, in the most speculative sense, be the technosignatures we seek, the artifacts of a technology so vast we mistake it for nature itself. The great silence of NGC 1300 may not be an absence of other minds, but rather a challenge to our own, a signal that we are only at the very beginning of learning how to see, and that the universe's greatest secrets require a wiser, more nuanced kind of listening. From its eerily silent central black hole that defies our expectations of cosmic violence to the enigmatic gamma-ray bursts that tick with a clockwork regularity no natural source should allow, NGC 1300 has proven to be a galaxy of profound and beautiful contradictions. We have journeyed through its strange heart, exploring 30 of its most baffling phenomena, the missing dark matter that challenges our models of the universe's scaffolding, the anomalous chemical patches that rewrite the story of cosmic enrichment, and the ancient, impossibly stable bar that seems to defy the very flow of time itself. We have witnessed ghostly light echoes revealing hidden structures, vast radio bubbles whispering of a violent past, and a great silence where we might have hoped to hear the signals of others. Each mystery, from the counter-rotating stars that speak of ancient collisions to the organized magnetic fields that sculpted space, is a piece of a puzzle so complex it humbles our current understanding of physics. This galaxy is not merely a collection of stars, it is a dynamic, evolving system that actively challenges the textbooks, forcing us to question everything from the nature of gravity to the fundamental behavior of the invisible dark matter that supposedly binds the cosmos together. These enigmas are far from mere academic curiosities. They are the very engines of scientific discovery. Every anomaly, every piece of data that doesn't fit our preconceived models is a precious clue. It is in these gaps in our knowledge that new physics is born, where we are compelled to invent new theories, build better telescopes, and think more creatively about the universe. NGC 1300 serves as a colossal cosmic laboratory, a natural experiment on a grand scale that tests the limits of our understanding. Its mysteries drive progress, pushing us to refine our concepts of galaxy formation, stellar evolution, and the intricate dance between normal matter and the dark universe. They remind us that science does not advance by simply confirming what we already believe, but by being persistently curious about everything we have yet to explain. This relentless pursuit of the unknown is what expands the boundaries of human knowledge and transforms the cosmos from a static picture into a living, breathing story that we are still learning how to read. Now, we would love to hear from you. After this journey through the strange and wonderful world of NGC 1300, which of these 30 phenomena captured your imagination the most? Does the great silence make you ponder our place in the universe, or are you more fascinated by the phantom ring of dark matter that hints at entirely new laws of physics? Share your thoughts and your favorite mystery in the comments below. Let's continue this conversation and explore the wonder of deep space together. If you enjoyed unraveling these cosmic secrets with us, please subscribe to the channel and hit the notification bell. There are countless more galaxies, nebulae, and profound mysteries of the universe waiting for us to explore, and we can't wait to share the next incredible journey with you.